Welcome back. Last time we were discussing torque, and I would like to continue that discussion today. So just to review, torque we can be loosely thought of as the ability of force to rotate something. It has to do with the amount of force that you apply, but also where you apply it and the angle at which you apply it. We can use the formula that torque is going to be equal to the lever arm R crossed with F to compute this torque vector. The magnitude of that vector then is going to be the lever arm times the force times sine of the angle between the force and the lever arm. And we didn't discuss it last time, but the units of torque can be easily deduced from these equations because we have a unit of meters and a unit of newtons involved here with the lever arm and the force. So the units of torque then we're going to call the Newton meter. Last time we talked about wrenches. Perhaps something more relatable would be these little hex wrenches that come in furniture assembly kits, and you may have had experience using these before. So what we want to know is what orientation will give us the most torque. So we could choose to grasp this hex wrench by this end and then rotate it about this axis, or we could choose to grasp the hex wrench by this end and rotate it about this axis. Or in this particular example, choice C is to get a weaker roommate who can only exert half of the force but who has access to a longer double length hex wrench compared to choice A here. So because the lever arms are different in sizes, then they're going to produce different torques. If you're applying the same force by grasping the hex wrench this way compared to this way, then you have a longer lever arm to work with, and so you're going to achieve more torque. Now sometimes it's easier to get a screw started by, this might be a quicker way to rotate it, to grasp it here and then twirl it around this way. But once you start needing to really torque it down, you will get a greater lever arm if you grasp it this way and then twirl it around. On the other hand, you might think that using the longer lever arm is the key then to getting the most amount of torque. However, the torque is going to be equal to force times the lever arm times sine of theta between them. If you are smart and apply your force at an angle that is perpendicular here, then you just have the force times the lever arm when theta equals 90 degrees, because the sine of 90 degrees is going to give me 1. So if your roommate has access to a hex wrench with double the lever arm, that's great. But if the roommate is only capable of exerting half of the force, then this turns out to be the same amount of torque as what you would have had if you had grasped it at this end. So that means that choice B here is correct, that the least amount of torque will result in grasping it here compared to here will give you more, and then your roommate exerting half the force with double the length of the lever arm would be equivalent. Of course, the best thing you could do in this situation then is to take that doubly length hex wrench and do it yourself, where you can apply the same amount of force as you were before. Okay, figuring out what the torque is one thing, but then we said that this analog to force in the rotational picture has an analog of Newton's second law for rotation. And that is that if we sum up all the torques at work on an object, then it should be equivalent to the moment of inertia times the angular acceleration, I alpha. So that is to say that the torque is proportional to the angular acceleration of the rotation and proportional to the moment of inertia. So the larger this moment of inertia is, the more torque you're going to need to achieve the same amount of acceleration. Okay, so we had started discussing an example where we were analyzing the net torque on something in order to figure out the magnitude of a torque that is produced from a crane's engine onto a drum. So last time we deduced that the magnitude of the tension T2 was going to be equal to the weight of the crate plus this acceleration rate. And so that gave us one equation to work with, but we are going to plug this into essentially Newton's second law for rotation. And so in order to use that knowledge that we had gained, we need to think about, okay, well, what was the net torque on the pulley? It's related to the force that's applied by T2, but it's also related to the force applied by T1. And we agreed that then, because of the direction of the rotation, T1 is attempting to produce counterclockwise rotation, where T2 is attempting to produce clockwise rotation, and obeying our sign conventions, that corresponds to choice A. So this is the net torque. By Newton's second law, this has to equal the moment of inertia of the pulley times alpha. Now, what is alpha in this case? If we think back to kinematics, we can recall that alpha has to do with there's a relationship where alpha has to do with the linear acceleration A divided by r. Okay, so we are given a linear acceleration rate, and we can use that then to figure out what the angular acceleration rate is. The linear acceleration rate is given here, and in this case, if we're looking for r, we're looking for r of the pulley. So this is going to be the same as saying I times A all over r of the pulley. Okay, so that's one application of Newton's second law for rotation as it applies to the pulley. And as I mentioned, we're going to need to do the same thing with the drum. So let's start with the equation that I just talked about. This is the left-hand side that we figured out on the last slide. This is my I, and this is my alpha here. Okay, the I was taken right from the parenthesis here. Okay, so that's the equation that I just had. Now we're going to apply the same idea to the drum. In this case, for the drum, think about what's happening. The drum was attached over here, and it had T1 on it, which was pulling this direction, right? So that would produce, if T1 were winning, that would produce clockwise rotation. Whereas the torque of the engine, which we're not really describing, exactly how that works, but the torque of the engine is attempting to move it counterclockwise, so you've got that positive torque due to the engine. This is the thing we're actually trying to solve for. So we don't need to break it down into force times lever arm. We just want to know what this torque is. Okay, so it gets a positive sign in our sum, right? So we're summing the torques here. And the tension, as I've just argued, is going to tension times that lever arm, RD, for the drum, will give me a negative sign. Then I'm going to, by Newton's second law for rotation, set this equal to I times alpha, right? And so I was given to us in the problem statement right here, and alpha is A over R, as I argued on the previous slide. Okay, and so now we have two equations for two unknowns. We solved for T2 already, and so we can actually figure out what that number turns out to be, and we can plug that into the first equation. And so then we can use that first equation to then solve for T1, which we can then plug into here in order to solve for the torque exerted by the engine. So doing all of that substitution, what we find is that the torque on the engine is going to equal 1700 Newton meters. So again, it's the same approach as what we were taking to Newton's laws when it came to the linear picture, where we look at all the possible equations and all the applications or directions of Newton's second law that we can look at. In this case, it was the rotation of both the drum and the pulley. And then we apply Newton's second law, and however many unknowns we have, hopefully we can come up with that many equations in order to deduce the quantity that we would like. Okay, we will continue this discussion in the next lecture.